Now, in this question, it's a little bit harder because what we're going to do, we want to break it up and solve separate parts and then bring it back and put it together. So we're going to integrate this function here, sine of 2x to the power of n and cos 2x all squared. Now, and we want to get down to this expression. So what we do is we work with the cos 2x all squared and convert it to a half 1 plus cos 4x. And notice that we come down to the half can come out the front. And we've got two expressions because we expand our bracket. And what we want to do is work those separately. We could also take the half and we could make that 2in out the front. So let's do this part first, which is sine squared and sine of 2x all the power of n. Again, we're going to use recursion with this and get in this form sine of 2x to the power of n minus 1. And then so we'll integrate the first, leave the second, and then integrate the first, derive the second. So, and then start to clean it up. So we get the n minus 1 out, the halves cancel, it becomes a positive. We get the n minus 2x there, and the cos 2x gives us cos 2x all squared, which if we look back we can see that that's in that form, except it's got the n minus 2. So that's really I of n minus 2 in that expression there. That part works out to be 0 when we do the substitution of pi on 2 for cos and sine. And the 0, they start to cancel out because we get a multiplication gives us 0. So there's the first part, comes down to n minus 1 I of n minus 2. Now the second part, which is cos 2x to the power of n and cos 4x, well, let's integrate that and see what we can get. So again, we get cos of 4x, integrate that, and keep the second one as sine 2x all the power of n. And then we have the integral of the first times the derivative of the second. So the n comes down, sine of n minus 1 2x times the derivative of sine 2x, which is 2 cos 2x. So, and then we can start to expand and clean it up. Get out a quarter times the 2 will cancel, and we get sine 2x, cos 2x, sine of n minus 1 2x will give us sine of n, because that's the power of 1. So that cleans that up. And the cos 2x gives us cos 2x all squared. We can put the n out the front with the minus, and we notice we're back to in. So that's minus in. So putting it together, two lots of in that we had before would be equal to n minus 1 I of n minus 2 minus the n of in. And then we can start to collect the in's together. We get the n minus 2, and then divide by the m plus 2, divide by the m plus 2 to give us the expression we want of n minus 1 on n minus 2 I of n minus 2. So we see how it starts to reduce there very nicely. Well, not very nicely. It's bloody hard. So you've got to be careful with it all to get to that expression. Then use that to calculate this one. So I4 would be the n minus 1 on n plus 2. So that's where the 3 on 6 comes from. I of 2, which that works out to be a half, and we get sine 2x all squared and cos 2x all squared, which means we can calculate that because we can get these expressions. Once we're at the squared level there, that's not too bad. So we get the half times of 1 minus cos 4x times half of 1 plus cos 4x, which is 1 minus cos squared 4x, which we can simplify to a half of 1 plus cos 8 of 8x, which then we can integrate. X 1 on 8 sine of x 8x, and do our substitution, and it all comes down to pi on 32 rather nicely. If you think that's nice. Now you can see how we're able to get to a point where we can break it all down and we can do our integration without having to do too much more work or reducing or reduction with it. So question 4. This time where our function is x cubed natural log of x to the power of n. And it should come down to this expression. So we integrate our first, leave our second. And integrate our first, derive our second. So we're able to see that we can do our substitution of e and 1. And we get to this point where we get e to the power of 4. Because natural log of e is 1, natural log of 1 is 0, so then we just get e to the power of 4 over 4, so that's where that comes from. That's nice. And we can take our n on 4 out, that's our constant. We got x cubed natural log of n minus 1, which if we look at that expression, well, that's very close. That's that's I of n minus 1 there. So that's where we can come down, and we've reduced our expression down to that. Because that part would be I of n minus 1, because it's just the same except powers n minus 1. So then, using that idea, find the value of 1 to e x cubed natural log of x squared. So we get e on, so we're looking at I2 really, because it's a squared there. E to the 4 on 4 is a half of I2, I1. And then I1 would be e to the power of 4 of a quarter I0. And I0 we can integrate, because natural log of power of 0 would be 1, so x cubed comes down to x power of 4 on 4, which is x cubed on 4 minus a quarter. So we can substitute all that. So we can substitute I0 back in there, I1 back in there, do our calculations to get 5e to the power of 4 on 32 minus 1 on 32. In question 5 here, firstly we need to do an algebraic manipulation. So we want to prove that these two are equal, so let's work with the right hand side. Looks a bit easier to manipulate, because we can do a factorization of 1 minus x to the power 1 minus root x power of n minus 1 out of side of both, which leaves us 1 there, and that would leave us 1 minus root x. And then we can simplify that to give us the root x. So there's our expression on the left hand side. Now obviously we're going to have to use that to express in the form of n on n plus 2 of I of n minus 1. So I of n, we can write it as 1 outside of 1 minus root x power of n. Integrate the first and leave the second. And between 0 and 1, which, not again, because you're going to substitute a 1 in there, that's going to give you 0, and when you put 0 into the second substitution, it's going to give you 0. And integrate the first, derive the second, so the n comes down, 1 minus root x power of n minus 1. 1 minus root x differentiates to minus a half x power of minus a half. So our minus a half n can come out. We've got then the root x, because x power 1, x power minus a half gives us root x. And we've got our bracket of 1 minus root x power of n minus 1, which we can do then our substitution here, because we proved that these two parts were equal, and then we can see that we get 1 minus root x power of n minus 1 minus 1 minus root x power of n. Again, we can see that this can be written as I of n minus 1 and I of n. Add the minus a half n, or add a half n I of n on both sides. Collect your terms and then do the division. And we can be able to get down to that expression there of n on n minus 2, n on n plus 2 of I of n minus 1. So there's our ways of reducing our functions to get down to an expression for an integral, where when we start to do the derivative and integrals of it, we find that it keeps coming back on itself. And if we keep getting to a point where it keeps coming back on itself, well, we're never going to be able to integrate it without that manipulation. So be careful when you see these ones. Make sure you're able to get it back into a form where you can get an expression for the integral itself that starts to reduce itself down and makes its definite integrals reasonably easy to calculate.